Hello. So, welcome to the next lecture on our discussion on sequential circuits. In the last lecture, we have covered the RS latch, which was one of the basic storage elements that will come in the discussion of our sequential circuits in the very beginning. And if you remember that sequential circuit is different compared to combinational circuits in the sense that the combinational circuits had an output which is dependent on the current set of inputs, right. So I'll just quickly reiterate. So this is combinational logic where you have outputs which is dependent only on the inputs, right. Whereas in some cases it might be that that outputs also could be stored in some way and be provided as a feedback to the above circuit as shown, right. So this is more of a feedback input. So this is primarily the structure where there is an input feedback, like the output is being fed back as an input to the circuit again. So this kind of circuit structure we call them as sequential circuits. The reason there is a temporal dependency, that is why often it is called sequential. Whatever is the output at the current stage, that output is going to influence the output for the next stage, right, or next state. So we gave you an example in the last class which was a counter, and I'm briefly recalling that a counter is a device or a circuit which counts from a number and in an monotonically increasing order to another number and then wraps around. So if you have a 3-bit counter, the maximum value that could be represented using these 3 bits is 7, 1, 1, 1, and it could start from 0. It could go from 0 and count upwards till 7, right, typically called an up counter, and from 7 it is going to reset back to 0 and again keep on continuing to 7 and again gets reset back to 0 and so on. So at any stage, if you ask me the output, that what is going to be the output at the next stage, I have to look at the output of the current stage. For example, if you have a counter circuit where your current output is, let's say, 3 or 0, 1, 1 in binary, the next output has to be 4. Okay. So if I know that currently it is 3, then only I can tell you the next output is equal to 4. So remember or notice that there is this temporal dependency of the outputs at a current stage with respect to the next stage, which is not true in case of combinational circuits. In case of combinational circuits, the current output only determines the current input determines the current output. That has nothing to do with what happened in the previous stages or what were the previous outputs. That is not required. So this is something that I kind of repeated, and this is something which has to be taken away from the course. This is a very important takeaway. What is the main difference in between a combinational logical circuits and sequential logical circuits? They have very different architectures and very different things could be achieved using them. Okay. So here if you see that there is a notion of a storage that we have mentioned in the last class, and we looked into cross coupled inverters as a starting example, and the cross coupled inverters had that Q and Q complement as two different outputs, but there was no apparent way to control that value of Q and Q complement, right. So we needed a controlled mechanism, and RS latch was the first one, right. So I'll not go into details of this because we have already covered it in the last class. This was a set of cross coupled NAND gates, and these cross coupled NAND gates, if we quickly look at the truth table, they have 4 possible set of inputs for reset and set. R and S stands for reset and set. Here specifically you need to remember these 3 things that are valid right? This is valid in case of an RS flip-flop. Valid inputs where if S and R are both 1, then it holds the previous state, or it acts as a memory element, right? So if both of R and S are does not change its value and that is set to 1, whatever was the value of Q, it is going to be maintained. Whereas you can have the option of setting or resetting the RS latch. You can set it by putting S equal to 0 while R is equal to 1, and we will show you how this is possible in the last class. There in that case Q is basically being set to 1, whereas if S equal to 1 and R equal to 0, in that case Q is going to be reset to 0. Okay. And one more very important thing that has to be remembered in case of an RS latch is, if you use R and S both equal to 0, this is not something anticipated, or this is called a forbidden set of inputs. It is not, the circuit is not going to behave in a logical manner or in a deterministic manner, I would say, if we put both R and S equal to 0. There are two reasons for that. The first one is that Q and Q bar, that is one of the basic assumptions that we have made while designing this kind of circuits or storage elements, that Q and Q bar are complements of each other. That has to be maintained, and if we put both of them at 0, that is not maintained. You can try it out. We have already discussed this in the last class. If what happens when R and S are both equal to 0. So first, that is not maintained, and the other thing is, if we have let's say Q and the R values change suddenly, right? So this is the first assumption, right? If R and S equal to 0, Q and QR will both settle at 1, which breaks our invariant Q is equal to naught of Q complement. So that is not something that is being maintained. The other thing that I mentioned was the metastability thing, where after being set at 0, 0, it suddenly, let's say they change their values. So they suddenly transition back to 1. Let's say S and R was 0 and 0, and S and R suddenly becomes 1 and 1. In such a case, as I told, you can revise, there is an oscillation in between the outputs of between 0 and 1 for Q and Q bar, which leads to a transient state or a metastable state, right? So this eventually settles back to values depending on the variation of the circuit. So if the top NAND gate and the bottom NAND gate, right, these two NAND gates have different propagation delays, which basically means how long does a signal take to get NANDed, right? So suppose you have A and B as an input to the NAND gate, and your output is A dot B bar, right, A dot B whole bar. So there it is a finite amount of time is taken to receive the output, right? And that finite amount of time may slightly vary from gate to gate as a like a hardware manufacturing artifact. Every hardware is different. So their gate delays might not be exactly same, and we are talking about nanoseconds, right? So somebody can take a little bit more amount of time, right? Somebody can take let's say 10 nanoseconds, whereas the other gate takes 11 nanoseconds or 9 nanoseconds. So based on the variation in these circuits, the value of Q and Q bar is going to be settling down, right? And which is very, very indeterministic for us as a user of the circuit. We expect a set of output for a given set of inputs, okay, or maybe the previous output. But you cannot really expect something that is metastable, and that is like not only transient but also the final state of the output is going to vary from circuit to circuit. That is not acceptable. Okay, so that is the reason we were not using 0, 0, because this leads to confusions, and that is why in an RS latch we use 0, 0 as a forbidden state. Okay, then we discussed the Boolean expression for the RS latch, and I asked you to do this exercise as given the S and R values, and we asked you to find out the value of Q. Okay, So this is something that you can simply, we already did in the last class. You can simply find out the Boolean expression and put the respective values of S and R in the Boolean expression, and this will be good enough to figure out what is Q next. Q next means the next value of Q given the current value of Q. Okay. So now we saw these issues with the RS latch, right? But how do you guarantee the correct operation of an RS latch? Because RS latch already had these nice three things where we were able to set the latch with a certain value, like with 0, or reset the value. Basically changing the value of Q is equal to 0 or Q is equal to 1 depending on our requirements. Okay, there is always this set reset. You might be confused, people might use different conventions and all. You have to remember that that value of Q could be set to 0 or 1 depending on the value of R and S. As long as you understand that, these confusions will not exist. And another point I would like to mention here is that if you replace this NAND gates by NOR gates, it will also be gate D-Latch or an SR latch or RS latch. You can try this out. This is like a homework that I would like to give to you, that instead of having a NAND gate, if you have a latch with NOR gates, okay, so you please try out what happens in that case. Okay, so you have Q, and similarly you have a NOR gate here. You have, this is Q bar, you have these two inputs, and then the other ones are cross coupled. Similarly, okay, so please try to see whether the thing remains the same or not, and whether you can achieve the functionality of this SR latch what we have studied. Okay, so similar or parallel things will always will exist for the NAND structure also, NAND gate structure also. And in the course of this lecture, so we are going to stick to the NAND structure. There is no specific reason for that. It's just that we have to take one of those NAND and NOR and proceed. Okay, so the conceptions are all the conceptually there is no difference in between them, and you have to just see what is the equivalence. Once you understand the equivalence, you do not have to analyze each one of them. Okay, so we are going to study next what is called a gated D-latch. Okay, so which is going to build upon the RS latch. So we have already studied RS latch, which is also shown in the picture here. This is your SR or RS latch is shown in the picture. We just want to have an extra condition that in a D latch it is going to be the same as SR latch or RS latch, just that S and R cannot be simultaneously 1. Okay, so just is one particular thing we want to touch upon here, such that this is the condition we want to impose. If if we are supplying S is equal to let's say 0, then R has to be 1. If R is equal to 0, then S has to be 1. That automatically takes care of the state where both of them are 0, which is basically the forbidden state. Okay, so D-latch captures the input data, what to set when certain condition holds, that is when to set, right? So if you look at the next line, is this D-latch captures the input data. The input data is what is the value that it has to be set with a certain condition when to set. Okay, and it operates in two modes, open or enabled. The input flows through to the output, or closed or disabled, output does not change. Okay, so that is a mode of operation. Okay, we'll come to all these things later, where you are enabling a D-latch or disabling a D-latch. But first understand the first point, where we are restricting what values S and R is going to take, and they are going to take complementary values. So from this description you can very easily figure out that S and R are kind of inversions of each other. Okay, that is something that is being mandated in a gated D-latch. So how does it, how will this going to look like? This will look like this. We want to add two more NAND gates, and as you can see that whatever is the value of D, right, we are trying to provide here, that is being provided as D here as it is, whereas there is an inversion here, this is D bar. Okay, so automatically this is going to mandate that S and R are going to take opposite logic levels. Okay, for example, we can think of let's say D is equal to 0 and write enable is going to enable whether we want to change the value of Q or not. So you want to say yes, that right, I want to enable that, otherwise you are not able to touch this circuit. If you, okay, just to recall, right, if we really put write enable is equal to 0, just to make sure that you follow the transition properly. So if write enable is equal to 0, what is the output that is going to happen in the two NAND gates? Because this is 0, one of the inputs is 0, the AND is going to be resulting in a 0, and then the output is going to be resulting in a 1 and 1, right? So if the inputs to the SR latch, right, because this is the, if you think of this as the module which is basically an SR latch, what is going to happen if you have both R and S equal to 1? This is going to act as a memory element, right? So if both S and R are going to be 1, the value of Q is going to be retained. The value of Q is not going to change, or it is not going to be tampered. Only if you want to tamper the value, you can put write enable is equal to 1, right? So if I really want to write, let me use a different or maybe I'll just use an eraser and erase this. Okay, so now I want to use it as a, not as a memory element, but I want to change these values. So write enable is equal to 1. I want to make the write enable set as high. So this is always at 1. And if I have the input as 0, right, if D is equal to 0, let's say, so 0 and 1 you do an AND, which is 0, and then an AND, so this becomes 1, right? Whereas this D bar is going to be 0, D bar is going to be 1 because D is equal to 0, so this is going to be 1, and write enable is 1, so 1 and 1 you are going to land up with 1, and then not of that, so you are going to have a 0 here. Okay, so in this case you can see what is the output. If you are basically setting S as 1 and R is equal to 0, this is going to result in Q is equal to 0. You can check it with respect to the truth table that has been drawn earlier. So S equal to 0 and R is equal to 1 results in 1, and S equal to 1, R equal to 0 results in 0. This is the RS latches truth table. Okay, so if here in our case S equal to 0 and R is equal to 1, so in our case here in this particular case S equal to 1, R is equal to 0. So you can see again one more time, S equal to 1, R equal to 0, S equal to 1, R equal to 0. So 0 is going to be the output. Okay, so S equal to 1, R equal to 0. In this particular case, Q is equal to 0. Okay, and if you take the other way around, if you, I mean, if you use a different value, if D is equal to 1, same thing, just that write enable is still at 1. So everything is going to be the same. So 1 is going to be 0 now, and this one is going to be 1. Okay, so this is going to be 1 now. okay, 0.1 and complement of that, and this is going to be 0, 1.1 complement, okay. So in this case this is going to be 1, okay. So what is interesting here is Q takes the value of D, okay. That is why sometimes this D also stands for like data latch or data latch. In this particular case it's called data latch. We are going to talk about flip-flops later. So whatever we want to write at the output, we simply pass on that value at D and make write enable is equal to 1, okay. So if we choose D is equal to 0 and make write enable 1, Q is going to be 0. If I choose D is equal to 1 and make write enable is equal to 1, then Q is going to be equal to 1, okay. So S and R can never be 0 at the same time. This is the one step improvement over the SR latch, okay. So this is called a D-Latch, and gated D-Latch. You can why it is gated, because the write enable is also going to help us whether to write or not, okay. So it's called a gated D-Latch, okay. So just remember there is nothing new here. We are simply building on top of SR, right. So as I told you, this module itself is the RS or SR latch, and we are putting a cushion over it, right. We are putting this extra gates before your S and R inputs and calling it a gated D latch. This is much more trivial to remember or understand. Whatever data you want to write, you just put that value. If you put 0, it will be 0. If you put 1, it will be 1, okay. So this is how the truth table might look like. So if we have write enable is equal to 0, so this is your hold state. It is going to hold upon the previous value that was already stored in the D latch. Only if you want to change the value, whatever value you put as D, so this is your write operation you want to do. So write operation is enabled, so WE is equal to 1. If I put 0 at D, Q will be 0. If I put 1 at D, it will be 1, okay. So hopefully this is this concept is clear. This is called the gated D latch. So I will digress a bit. There is a new concept that has to be understood in order to move on to new kind of circuit elements, which are sequential circuit elements called flip-flops. So we want to introduce you to the concept of a clock, and as I told you that in a sequential circuit there is a temporal concept, that what happens next, what happened before this, and so on. So we need a mechanism to keep track of time, right, because as time progresses, the circuit also needs to know that time has progressed, right, and we need a way to determine the sequence of these times, right, some kind of a resolution at which we are keeping track of time, right. There is no concept of minutes or seconds or milliseconds or nanoseconds in a digital circuit unless and until we define one, okay. So we need to define something which keeps track of time and also determines the discrete time intervals when we expect the next phenomenon or the next event to occur, okay. So this is done by using a clock, and this clock is an input to the sequential circuits that changes output states at a predetermined rate. So this clock, this has these two states. One is the high state, high or 1, logical 1, and this is the low state, low or 0, okay. So this is an input that is fed to a sequential circuit, and we can always count the number of highs and lows, right, per unit time, right. So that could determine that how fast or how many times the clock has been given to the particular circuit, okay. So this clock can operate at a certain predetermined rate. So you are seeing all this the waveform. So they have two parts, right? One is this positive or rising edge, right? Once you have a value of 0 and it wants to go to a value of 1, this is something which is called the rising edge. And once it is 1, it wants to come down to 0, right? This is this direction and this is the upward direction. This is called the falling edge. So these two terms are important. And once it comes to the lower stage, right, it comes to logic 0, it stays for some amount of time, which is called t low, time low. And the time it is at a higher stage or higher logic level, it is called th. And these are not necessarily the same value. Okay, so we have some value for th, we have some value for tl, and there are multiple ways to or multiple applications where this ratio of this TL by TH plus TL could be changed, and it has other various applications, right? We are not going into details of that, but at least what you can understand that this one particular cycle, that is from this blue line to this blue line, this constitutes of one cycle, and you can have n number of cycles per unit time, right? Unit time could be 1 second. In 1 second you can have, let's say, 50 such cycles. That means that the clock is operating at 50 hertz. Okay, so so this 50 hertz, you basically have this 50 units of time that has been spent in the circuit, right? So you have this clock, and this clock outputs this waveform which is being fed to the sequential circuit. Okay, so the sequential circuit is going to change its state, right, with every pulse that is being provided. Typically we use the positive rising edge as the triggering edge in this particular course. So whatever we are currently discussing, we will stick to one particular trigger which is low to high, although the triggering could be done in high to low as well, but we will stick to one particular convention. So this is being counted as one trigger. That so if you expect the circuit to go to the next state, it is going to spend this time to go to the next possible state. Then the next trigger is going to come here, the next it will again advance to the next state. After that there might be one more trigger here, the circuit will advance to the next state. So in this way, for every time the clock pulses or the clock cycles, the sequential circuit is going to move through a sequence of states. Okay, and this is what we call the clock tick, the occurrence of a triggered edge. So this is a triggered edge. This is going to count as a clock tick. Okay, so you might have a fast clock which basically ticks more number of times per second. So you might have a clock that operates at 20 hertz, which basically means that there are 20 ticks per second, okay, which is one tick per, let's say, 50 milliseconds. Whereas you can have a clock that is operating at 100 hertz, right? So 100 hertz means one tick per 10 milliseconds. Okay, so if I draw, let's say, the diagram, so this is 1 second, 1 second. If you have a clock that is operating at 100 hertz, you will have something like this. So if this is 100 hertz, your entire cycle is about 10 millisecond. Okay, and if you have a circuit that is operating, let's say, at 10 hertz, let's say 10 hertz, so this will be more relaxed. So you'll have 10 occurrences like this. So each one is going to be 100 millisecond. So 100 millisecond multiplied by 10 is equal to 1 second. That is how we are getting this. So here you can think that you are supplying this 100 hertz clock. So in 1 second, the sequential circuit is going through 100 state changes. right? Given that for every clock pulse you are doing something in the circuit such that the state changes. Suppose you are just say changing S and R values to an RS flip-flop, and you are basically at this 100 times per second, right? Whereas you are trying to do the same but at a much slower rate with a 10 Hz clock. Okay, you can imagine that this particular write enable that we had in the gated D-Latch could be used as a clock, right? So that could be the frequency at which we can change the value, or we can write values to the latch. So if I go to this particular diagram and we connect this write enable to, let's say, a clock, okay, and the clock pulses like this. So sometimes the write enable is 0 and sometimes the write enable is 1. So the frequency at which I can update the value of Q depends on the frequency of the clock. So more the number of states per second we are able to put in the clock, faster is going to be the operation of this particular D-Latch, and we are going to process more values or update the values at a faster rate, which is required for computation. Later we can understand that we can use these latches for designing memories, right? We already gave you an example of SRAM cell. I want to write faster to the memory, I want to read faster from the memory, all depends on this clock. Okay, that is the reason I started speaking about the clock. And the other thing that you need to remember is that we typically talk about the clock tick here, okay, occurrence of a triggering edge. We are not talking about this particular level here, because we need to understand that also, because triggering edge is something that we want to capture in the rest of the sequential elements which are not latches. So the transition of the clock that captures the input data. So earlier in this particular example, we are capturing the data not on the edge triggering. We are capturing the data when the clock is high. If the write enable is 1, if I am calling it WE, if write enable is equal to 1, then we are activating, then we activate, etc. Right? We are reading, or we want to do, we were writing the value of Q and so on. But there are some issues that we will discuss very soon, and we do not just want this to be restricted to the level of the clock value, right? If we just replace this by a clock, we do not want to execute read write operations or write operations here at this entire set of interval, right? So this is the red marks allows any writing, right? This is where you are enabling writing. Rather, what we want to do is not put it there, right? I will draw one more parallel clock. We want to restrict our write enables only into these zones. Okay, so these are called edge triggers. Okay, whereas this is called level triggers. Okay, there is a difference. We want to make sure that the circuit is activated only at the edge of a clock, versus earlier the way we were doing it, and if you put a clock in this write enable, we are just using the level output of the clock as the enabling or as the enabler of the gate. Okay, this is what we meant by edge triggering or triggering edge and clock ticks. So this is something that I already told you. There is a clock period or a cycle time and a clock frequency depending on how fast this clock is operating. So I gave you a few examples. If the clock frequency is given, you can find out the cycle time and vice versa. And this is something which is called the duty cycle. Just now I told you that the ratio of this TL and TH, there are some applications. I am not, if you are really interested, you can ask us later, but this is not a very important discussion in this particular context right now. there are multiple applications how changing this high time as a with the ratio of this can be changed, and there are some potential applications. You can look up things like pulse width modulation, PWM, and so on if you are interested. Okay, so typically this is called duty cycle. Okay, we can keep it to 50%. For our case, there is not much of a headache unless and until I want to design a circuit that has a different duty cycle. Okay, in our case, we are simply restricting ourselves to the event of a positive edge trigger. As long as we have these triggers, these are the points that define the state change of our sequential circuit, we are happy. Okay, so this is the concept that I wanted to give you regarding the clock. Okay, so regarding the clock inputs basically. So now let us look at the timing of the D-Latch. We just introduced you to the D-Latch already. So now let us look at the timing of the D-Latch. This is a timing diagram. So here this axis that is drawn here is time. Okay, and these are the logic levels. So this is 0 1 0 1 or 0 1. This is the top one is the clock, the next one is D, the next one is Q. Okay, so now we are all familiar with this particular circuit. We know that if clock is equal to 0, which is being used as right enable, the way we just now said, if right enable is 1, in that case what happens? If if right enable is 1, in that case D is copied to Q. Okay, so if you see in this particular circuit, this is the times where the clock is enabled, the clock is the right is enabled. Okay, so the value of D can change any time. Okay, there is nothing we can control about it, because this is some kind of an input that is coming from an external source or some other circuit where the value of D has to be written to Q. Okay, so you can see that this value has some inherent asynchronicity with respect to the clock. The clock operates at its own, and the value of D also comes on its own. So there is nothing that is going to be respected with respect to this triggers and so on. So this value was 0, suddenly it became 1, and then again it was 1 for some point, some period of time, then it became again 0 and so on, and then it remained 0. Okay, and what does this Q do? The Q is going to follow the input D only when we have a enabling clock, right? So as you can see in this part of the figure, let me use some other color. So in this part of the figure, right, where the clock was closed, the change was not reflected. Okay, this is Q, but Q is not going to listen to D if the value if the right enable is closed. Okay, in this part this is clock is equal to 0. So if you can see that this change was not reflected. Whenever it opened one more time, in that case only it is going to get reflected. Okay, so later it got reflected, and again after that it did not change its value, it also did not change its value. Okay, the problem with this particular thing is that it is highly asynchronous, right? So it is very difficult to have the values of D and Q deterministically reflected, because the clock in this particular fashion does not have any synchronicity with the inputs. Okay, so captures the input D when the latch is enabled and holds the previous state otherwise whenever it is closed. Okay, so we call this is level sensitive. Okay, there are many applications that is okay with the D-Latch, but particularly when we are really careful or when we want to do something across multiple circuits and I need to follow a certain global timeline, in that case this is not very good, because these times could be fluctuating because of various reasons. The closed interval and the open interval, that could slightly change, right? And depending on that, the values of q is going to get changed. Okay, so this could give rise to some asynchronous behavior in the circuit, which could in some cases is very difficult to handle or difficult to debug in most of the cases. Okay, so we are going to look into an alternate way where our circuits are no longer level sensitive, but it becomes edge sensitive. So currently all the latches, LATCH, these are level sensitive devices. Okay, level sensitive devices. We also, and that has this problem of this asynchronous inputs and outputs, because the clock is also I mean the say inputs or the inputs rather are not really synchronized with the clock and so on, and this the amount of time the clock remains bigger or like a high state or a low state, that could slightly fluctuate in some cases. So the output also becomes a function of the time the logic of the clock is high, right? So it is also a function of the this timing. Okay, sometimes it cannot be guaranteed precisely in a chip circuit. In that case, the value of the D rather is kind of sometimes cannot be relied on depending on the application. Okay, so rather we would often like to go with a circuit which is not dependent on this time but dependent on these edges. Okay, so we will look into a device called flip-flop, right, which is edge sensitive. Okay, so these are edges. Okay, so edge sensitive storage elements are called flip-flops and D flip-flop. So we are going to look into how a D flip-flop works. So this is nothing but just two D latches connected back to back, and the inputs are D, which is your data, and the clock, and the output is Q, which is the same. There is no difference in between the functional, the way it behaves from a user perspective. You still give a D and you still get an output Q, but the system makes sure that it only writes at a edge triggering. Okay, it is no longer level sensitive. It only depends on whenever the clock changes its value from 0 to 1. Okay, or 1 to 0, then that is becoming a high to low edge. We are going to concentrate on one kind of edge triggering. There could be also dual edge triggering, where you trigger the circuit both at a positive edge as well as a negative edge. We are simply not going to touch upon those concepts right now because of the there's a lot of things to cover. We'll just cover the cases where you are only having a positive edge trigger. So captures the input, which is basically copy D to Q on triggering edge of the clock. Otherwise, when the clock remains steady at 0 and 1, it retains its value. This is very important. If the clock's value is just 0 or 1, nothing happens to the circuit. Okay, which was not the case in case of a D-Latch. If the clock's value is 0, then your circuit is like nobody can tamper the value. But when the clock is 1, which is write enable is equal to 1, then whatever is the input coming, it is immediately going to reflect on the output. Okay, so this is the basic definition of a flip-flop. In the next lecture, we are also going into details of D flip-flop, how it works, and there are several kinds of flip-flops we are going to study. One of them is JK flip-flop. We are going to study that in details. And these are the building blocks of memory elements like registers and so on. Okay, so I'll keep it till here.